Okay, today we're going to talk about the last quantum number, and I know the video got to it and we didn't. Sorry, I'm a little slow on that. But they discovered in the 1920s, so 100 years ago, that two electrons in the same orbital, they're a little bit different. Okay, they don't have exactly the same energy. And what they found is um, if one is spinning one way, one has to spin the other way. So the last quantum number is called the spin quantum number, and it tells you which way they're going. And it's either plus one half or minus one half. It's either spinning clockwise or counterclockwise. And the thing about it is the spin is affected by the energy. So if one comes in going one way, the other has to come, it has to be spinning. They can't spin the same direction. And if they do that, what they'll do is they'll kick each other out. It's kind of like a magnet, if you put the two north ends together, they push each other away. But if you put a north and a south, they stick together. That's kind of the same thing. So they have to be doing the opposite. And then that way they can stay in the orbital. If they're spinning the same way, then they're going to push each other out. Okay, so that's the spin quantum number, and they say it's m sum s, and it's which way they're spinning. And again, it's either plus one half or minus one half. That's it. That's the only two numbers. So if one is spinning one way, when the other one comes in, it has to spin the other way. So that's your four quantum numbers. And again, quantum numbers describe orbitals. Orbitals is places where you find electrons. Okay, so the first one again was the principal quantum number that tells you at what level. 1, 2, 3, 4, 5. The bigger the number, the farther they are from the nucleus. Okay. The second one was called the angular momentum. I wish they would just call it the shape, because that's your SPDF. That tells you the shape of the orbital. And then the next one is the magnetic one, and that actually tells you their orientation. And then the fourth one, excuse me, is the spin. And again, that's which way are they spinning? It's either plus one half or minus one half. That's the only values they have for it. Okay. So if one's at plus one half, the other one has to be minus one half. And again, they cannot be spinning in the same direction. They'll kick each other out. Their repulsive forces will push each other out of the orbital. Okay? We don't have to watch that. Okay, so we're going to start writing what they call configurations for electrons. We can write a configuration to show you exactly where every electron is in an atom. And people are like, so why? Well, if you're going to do a reaction and you want to make a compound, you have to see where there's space available. Okay? The more space that's available, the better you have, or better luck you'll have if you're going to come up with a compound. So you got to look at where the electrons are and if they'll combine. Okay. One of the first rules when you're doing electron configuration is something called the Aufbau principle. Okay. Aufbau was a German guy. And he said that electrons go in the ground state. They have to fill the ground state first. In other words, if you have level 1, you cannot fill level 2 until level 1 is filled. And then once level 1 is filled, then you have to fill level 2. And once level 2 is filled, you have to fill level 3. You can't start filling level 4 unless 3 is full. Okay? And you can't fill 3 until 2 is full. And that's their ground state. We talked about that, where the electrons, they always want to go to the lowest energy level first. Okay? That's the way they do it. They fill in the lowest energy level first, and then they go to the next one and the next one and so on. And if you keep that in mind when you're doing the configurations, the nice thing about that is they're always in the same order then. And again, I'll show you how to do this. We'll have a video with the hands, okay? All right, so again, Aufbau principle says electrons always go to the lowest energy level first. You got to fill the low ones, and they go in order after that, okay? And then the Pauli exclusion was on the video. It says no two electrons in the same atom can have the same four quantum numbers. If they're in the same orbital, they will have the same principal quantum number. They'll have the same angular momentum. They'll have the same shape. They'll be on the same orientation, the magnetic, but their spins will be different if they're in the same orbital, okay? So that you can't have two electrons with the same four quantum numbers, okay? So they can't be at the same exact energy. They're just a little off. And again, I'll show you how that works here when we start doing electron configurations, okay? This means that every electron in an atom has its own four quantum numbers. No two electrons in an atom have the same four quantum numbers. So the principal quantum number might be the same, their angular, their magnetic, but then their spin is going to be different. Okay, so they can't have the same four quantum numbers. That's why we have the plus one half and the minus one half when we get to the spin. Okay, all right, and then there's another one called Hund's rule. So there's three rules. There's the Pauli exclusion, they can't be the same. We have Aufbau, they go to the lowest energy level. And then there's one called Hund's rule, okay? And if you look at Hund's rule, what happens is when you're filling these represent an orbital, the boxes, and then the lines represent electrons, okay? And they go in the same order all the time. So 1s is first, and then 2s, and then there's 2p. Now remember, there's only one s orbital, but there's 3 p orbitals. There's an x, a y, and a z. Okay, so what happens is when you get to this point, some people want to, okay, I got these two filled, I'm going to put these two together and just leave these off. And you can't do that. What happens is, what Hund's rule says is when you get to an orbital with equal energy, so the p's, they go in one at a time. Okay, see how it's 1, then 2, then 3, and they don't double up until they have to. I call it the apartment rule. If you think about it, if there's 3 of you guys and you get a 3-bedroom apartment, everybody gets their own room. Why are you going to double up and leave a room empty if you don't have to? Okay, so Hund's rule officially says when filling orbitals, the lowest energy is obtained when the number of electrons have the same spin maximized. Or, like I said, they go in one at a time and they don't double up till they have to. All right, and again, I'll show you that when I start doing the configurations. But those are the rules we have to remember: Aufbau, Hund's, and Pauli exclusion. Okay, and here again, means that the 4 set of orbitals on the same sublevel have to have 1 electron in each before pairing up. Okay, and they'll do that. They'll separate out. Okay, these 2 guys won't go in this orbital and leave these guys empty. All right, so when you're doing these, and again, I'll show you these, you have to remember these rules. All right, here's an orbital diagram, and I'll show you guys today how to do these. What this box represents, and honestly, when I do them, I just do lines because that's a lot of boxes to draw. This represents an orbital, and this represents an electron. Okay, so if you look at lithium, its atomic number is 3, and it starts at the 1s. That's the first level. This is actually hydrogen, and then this is helium, and then you get to lithium. And again, it just follows your periodic table. I'll show you how to do that. Some of you guys might have remembered this from high school. I don't know. And again, the reason why we have one arrow going up and one arrow going down, spins. Remember, they have to have opposite spins. So we can't draw them going in the same direction because they won't do that. Okay, the direction of the arrow represents the spin. So this 1 is the principal quantum number. This is the first level. This is 2. It goes down to the second level. That's where lithium is. The S represents the shape. Okay, and the orbitals, we really don't have the third one because an s orbital right now doesn't have any more than 1. Okay, if we got to the p's, then we'd have more. That would be the third, and then this would be your 4th quantum number. Okay, all right, so once you learn how to do orbital notations, and that's what I'll show you first, the next thing is called the electron configuration. And the way you do that is, it's kind of a shorthand way of writing them out. And again, I'll show you how to do those in a little bit after this. So I guess we're just kind of going through the notes, and I'll explain it more later. But we have to make sure we have the most stable, the lowest possible energy level. And again, that's the ground state. And that's what we talked about. They always fill the lowest one. So when we're doing electron configurations, when we're doing orbital notation, we're doing them all. We always start at the beginning, 1s. Because that's the lowest, and then we move to 2s. The order is always the same and never ever changes. Okay, so when you have a component, like here we have 4p5, okay, the 4 is representing which level it's on. It'd be on the 4th period, the 4th period, the 4th row. Okay, that denotes the energy level. Okay, the p we talked about, that's the shape. Okay, so this is a p orbital. Remember the dumbbell shaped ones? Okay, there's 3 of them. When you go to the 4th energy level, there's going to be 3 of these p orbitals. All right, so in the electron configuration, again, we got to fill the lowest possible energy, the ground state, first. So the next thing we have is the p, and that's the letter denoting the shape of the orbital. Okay, I don't know why they keep doing the same things over again. And then when we get to this one, okay, this tells me how many are in there. See, now the p orbitals, there's 3 of them. So each of them can take up to 2. So the max that the p can have is 6. All right, they can have 6 electrons. This p has 5. All right, so I have room for 1 more. Okay, so the s can have 2. The p can have 6, and I'm talking about number of electrons. The d, there's 5 d orbitals, so that means they can have 10 electrons. And there's 7 f orbitals. That means they can have 14. So that number there is, that's the max they can have, but they can have less than that if they haven't filled them up. Okay, so there's also what they call condensed electron configurations. And again, I'll show you how to do that. You'll see them right here. And what they do, I've always called the noble gas configurations. The condensed means the same thing. It's really based on what happens here is if you go to potassium, if you go to the row above it, the noble gas at the end of the row is argon. So you put it in parentheses and it means everything the same as argon and 4s1. This would be the condensed configuration for potassium. And again, I'll show you how to do that. But it's based on the noble gas at the end of the row before it. You write that and then you continue with the configuration. This is really nice. It's not so much for these first guys, but when you get down to these big ones, these configurations are super long. Okay, you have to write the configuration for 87 total electrons. And so if you can write it this way, it makes your life a lot easier. And again, I'll show you how to do those too. Okay, so you have your filled inner core, the D and the F, and again, I'll show you how to do that. It's all based on the periodic table. So if you have a periodic table and you fill in your periodic table, and I'm going to show you how to do that, and follow your periodic table, these are really simple. Okay, all right, so this is the shorthand version. So we have what they call the orbital notation. That's the first one, and I'll show you that one. If you figure that one out, that's the longest. Then you have the electron configuration. Then you have the condensed, or what I call the noble gas. And then they also have a dot one, but all of them are based on each other, and if they get less and less complicated as you move down the line. Okay, here's one for the transition metals. Again, here's your energy levels. The weird thing about it is you'll see they don't go in order. You think it'd be 1s, then 1s, 2s, 2p, then 3s, then it's 3p, and then it's 4s, and then it's 3d, and you're like, wait a minute, why does 3d come after 4s? And there's a reason for that. It goes by their energy level, not by their numbers. Okay, you'll see right here. If we're going in order, we got 1s, then we get, these are the orbitals in order. 1s, then 2s, then 2p, then 3s, then 3p. That's all makes sense. We do a 4s, and then we go to 3d. It's like, wait a minute, shouldn't that be 4d? Nope. And the reason for that is 3d actually have higher energy than 4s. And again, I'll show you how to do that on your periodic table. It's the transition metals that for some reason their energy level, even though they're a 3 as far as their notation, they're actually at a higher level. So 4s comes first, then 3d. So they don't go in order. Okay, they've got it written like this. And again, I'll show you how to do that here in a bit. Okay, when you look at the bottom, the lanthanides and the actinides, those rare earth, those are the Fs. Okay, if you count them, you'll find out that there's 14 of them. That's 7 orbitals, 14 electrons. Okay, and they're actually supposed to be in the middle of the periodic table. Do I have my periodic table? Okay, if you look, the first lanthanide is 57. Well, if you look on your periodic table, you got 56 is barium, and then it goes down there to 57, and then you'd come back up again. And the reason why they're not in your periodic table, it would just be too long. And these guys are kind of mostly man-made elements, so they just kind of put them on the bottom. Okay, so the first is the lanthanide series, and then the actinide series, and these are the Fs. So if you're at barium, and then you'd have to go down to F and then come back up again. And again, I'll show you how to do that when I talk about configurations. Okay, here's your orders. So these guys are the S's. These guys, and well, this is helium. Okay, helium would actually be over here when you're doing electron configurations. And then this block is the P, so this would be like your halogens and your oxygen families and all that. These are the transition guys. These are like from scandium over to zinc. And if you look right here, see, this is the reason why the Fs aren't in there. Look how long it makes the periodic table. So they plop this over here and they stick them on the bottom. But again, this is where they would be if you go by number. And again, I'll show you how to do that shortly. So you fill in the orbitals by increasing energy, and it's always the same order. It never, ever, ever, ever changes. Okay? And the S and the P are the main groups. Those are the ones we work with mostly because those are the most common elements. We don't really work with uranium and plutonium and all those other ones, but they're there, and I'll show you how to do them if you have to. Okay? Let's see. We're just about done, so we'll quit right there. Okay? So again, I'm going to show you how to do all these configurations. I suppose your head's probably spinning a little bit right now, but I promise I'll make it make sense to you. All right?